Hello, this is the recording for lecture number 4. This is the point where we start kinetics of particles. Kinetics of particles considers the force-motion relationship. Up to now, what we have seen in kinematics is motion-to-motion relationships. Basically, we're going to make use of Newton's law, F equals ma. And then, in the next lectures, we will take the integral of this equation and we're going to integrate it with respect to displacement and receive work energy equations, and thus we will work on the work energy principle. Then we'll use the same equation and integrate with respect to time. As a result of that, we'll get impulse momentum equations. We're going to define the impulse of a force and then the change of the momentum as a result of this impulse. At the moment, for just particles, we'll apply this F equals ma equation. You need to be careful here that the equation is a vector equation. Forces are vectors and the acceleration is a vector. M here is considered to be constant, so this is our assumption in this evaluation of particles in terms of their kinetics. Now, in terms of units, we're using newtons for force, and based on this equation, this newtons is kilograms meters per second squared. This is the SI units. Please do not use SEC, for example, for the let me try to use the pencil. For seconds, this is not SI units. If you use SEC, we use S for SI units. N is capital because it's the guy's name, Newton. Kilogram and meter and seconds are not any guy's name, so they are in small caps. Now, generally, we investigate dynamics in two directions. We have two problems in dynamics. One of them is the direct or forward dynamics. The other one is inverse dynamics. The assumption in direct dynamics is that the forces are known, and as a result of that, we are trying to find out the consequent motion. In inverse dynamics, now the motion is known. The characteristic of the motion is known in terms of position, velocity, and acceleration is being the most dependent variable for this investigation. If the motion is known, then we are trying to find the corresponding forces. Why we would use direct dynamics is for modeling purposes, because now you have, as you do the analysis, you have developed the equations of motion, and you have a working simulation model of your system basically. And as you apply forces to the system will start moving. So basically, direct dynamics would be used for modeling purposes. Inverse dynamics, on the other hand, is used for design purposes mostly. You want to generate a certain motion, and for that motion you want to figure out what kind of forces you should apply to your system, rigid body, or the particle in this case. And by finding out these forces, then you are able to select the actuation system, which could be an electrical motor, for example. So you use this information in your design purposes. Other than that, you find out the reaction forces, for example, and these reaction forces would give you the information about your design, select your materials for the links, for example, in a mechanism. And this inverse dynamics is also used in control. This is what you're going to be seeing in the next year's course, System Analysis and Control. We have already defined different type of motions. We know what an unconstrained motion is for a particle. If we are defining this in a three-dimensional world, it's the translational motions of this particle in space in x, y, z directions. If there's a physical guide, then the path is defined with respect to this physical guide, and this path is defined by forces acting on the particle. We usually call these forces constraint forces or reaction forces. The example that we had in the beginning of this course was this spherical ball, the sphere, the steel sphere, if you remember, and then it was constrained to move on a straight path. And the reason that it can move on that straight path is that two of its motions were constrained by this path, so it can just do a linear motion. And the constraint forces are due to the guide, actually, the physical guide. If the physical guide doesn't exist there, the ball will just fall. And the reason that it doesn't fall is the normal forces that are applied by the physical guide to this sphere. And that brings us to the constraint motion. The path is totally or partially determined by these physical guides. You can define actually the planar motion of a particle as a constraint motion, because the constraint in this case is the plane itself. The plane applies normal forces to the particle so that the particle cannot move inside or outside the plane, but it stays on the plane. Or you can define it as a 2 degree of freedom unconstrained motion, if you like, or a planar unconstrained motion. In free space, like we said, we have three degrees of freedom for particles. The reason that it's not 6 degrees of freedom is that the particle has a negligible dimensions, and as a result of that, you don't really consider its rotation, so it's just translational motion. If it is constrained to move on a surface, it will have 2 degrees of freedom. If it is constrained to move on a linear path, it has 1 degree of freedom. And this was the example of the sphere, the steel sphere that we had. Now the first part we're going to consider is about rectilinear motion. It's the motion along a straight line. This straight line could be in the x-axis, or in the y-axis, or in the z-axis. Remember that you are the one to select these coordinate frames. So let's say that we have a straight path. Let me just try to draw the straight path here as best as I can. So let's say that this is a straight path. Then you're free to choose your axes. Now, if you choose one of your axes, let's say along the direction of the straight path, let's say that this is the y-axis, and then you have this x-axis defined. Okay. Now let's say this is the x-axis direction. Then the motion happens along the x-axis, and therefore the acceleration will be along the x-axis. Ax will be a, and there will be no motion along the y-axis. So all this motion is along the x-axis in this direction, let's say. No motion is along the y-axis or z-axis. Therefore, the acceleration in those axes will be equal to 0. That means the motion along those axes are constrained. There should be a static equilibrium in that case. That means there should be these forces acting on the particle based on these constrained environment in the y and z axes. And the basic example for that is if we have a plane, let's say that this is our plane, okay, and then we have a particle. The particle is on the plane, and then the particle has a mass, and as a result of that, there is this mg, the gravitational force acting on the particle. At the same time, the plane applies a normal force to the particle so that the particle stays on top of the plane. But how about the acceleration of that particle along this vertical direction. It's equal to 0. So if you write out the summation of forces in the vertical direction, let me just identify that by V, Fv, then it will be equal to, let's consider the upward direction as positive, so N minus Mg would be equal to 0. No motion, that means. This is what you have learned actually in the statics course. This part is about statics. But then the particle can have a motion on top of the plane like this. So it could have a path like that. In that case, now the summation of forces in the x and y directions, let's call them x and y now, will not be equal to 0. Not necessarily. It could be if there is no change in the velocity, but they are not equal to 0. Not necessarily equal to 0. Summation of forces in x and y. And if it happens that it has a linear path, then you might as well choose your path in the direction of the motion. So instead of getting two scalar equations that are not equal to 0, you will get a single equation that is not equal to 0. But again, you're free to choose this axis. Even you can choose a system, a coordinate system, so that, let me just try to draw this coordinate system for you. Okay. Can find my pencil. Okay, here in the pencil tool already. So here is our x, y, and z axes. Now the motion could be in this direction, and because you already choose your coordinate frame not in the direction of the motion, not any of the unit vectors of this coordinate frame are in the direction of the motion, then you will get accelerations in all these three directions, and you might as well get fx is equal to max, fy is equal to may, fz is equal to maz. And you need to solve this problem by using these three equations, which is not very convenient. So the better choice for a rectilinear case is to choose one of your coordinate axes in the same direction of the motion. So this is about it for the rectilinear motion. We're going to continue on with the curvilinear motion in the next video.